I don't really have a lot of results though, but I mean, I'll talk about what exactly the general idea about the whole work is, and then there are some interesting results that people have found, and then we are trying to extend this and what exactly we are trying to look for, and maybe something else comes up. So okay, so this is about superconductivity, and the rest of the words over here you will get to know what exactly, as I'll explain all this. Okay, so starting with the history where this Hamiltonians first found this superconducting behavior in 1911. So he was the first one to liquefy helium. So he had all the tools and everything, and then he thought, okay, let's just see what exactly happens to the resistivity, because it was an open question and nobody knew, because nobody went to that low temperature then. So everyone wanted to know what exactly happens to the resistivity as we go down in temperature. So he saw that there's an abrupt change, that it goes down to zero, essentially zero, and then it continues for this thing. So this is the first observation of superconductivity in 1911. And then people started looking for other phenomena also, that this is not just zero resistivity, but there are other fascinating effects, which is one of them is Meissner effect. Meissner effect is, of course, it has a lot of applications. The initial photo that I showed you, this is the Meissner effect. You might have seen a lot of videos and all these things on YouTube. So it turns out that people, if you look up the internet, people try to give Meissner effect a very classical explanation, but it's not really true, because the thing is, if you just take the Maxwell's equation and you say, okay, superconductor is nothing but a superconductor where your resistivity just goes to zero. What it says is that the change in magnetic field inside the superconductor should not change, but it doesn't say anything about it being zero. So you can't really get Meissner effect just by using classical arguments, just simple calculation. But so it's truly like a quantum phenomenon, and it turns out that it actually is the defining property of superconductor. So starting from Meissner effect, you can explain why you have this zero resistivity. I won't really go into that, but this is just for the thing. So there are other properties also. There's one that I'd like to talk about, which is the isotope effect. This is interesting because it gives you a hint to where to start from, where if you want to write down the microscopic theory of what exactly is happening to the materials when it goes to the superconducting state. So what it says is that the transition temperature where it becomes a superconductor, that is inversely proportional to the square root of the mass of the lattice atoms, right? So why would anything that has something to do with the electronic property would be linked to the lattice of this thing? Just think of it that way. So if you remove all the electrons from the system, you have only the lattice left. Now this under root of m has some idea, it tells you something about the lattice vibration, right? And lattice itself is not really, it's a very boring system, but it can give you phonon modes. Phonons are basically the excitations or the vibrations in the lattice. So it has something to do with the lattice vibrating and electron coupling. So that is the central feature for the mechanism of superconductivity, and that's where you start from writing down the microscopic theory, and that's what BCS did. So they started with the Hamiltonian, where you have just the usual energies due to the phonon modes. This is just counting the number of phonons in the system and the energy related to that, because it's just the quantum harmonic oscillator. And then you have the energy related to the electrons in the system. And then there's this electron-phonon coupling. So this is, you can think of this as, okay, this diagram is not really that. So you can think of it as, electron absorbing one phonon and then changing its momentum. So the momentum, just think of, this conserves the momentum and all the other way can give rise to a phonon as well. So yeah, this is the coupling which gives rise to this superconductivity. So you can think of this as like perturbation theory, and then think of this M cube to be very small, and do a second order perturbation theory, because first order turns out to be zero. So but it's not really that. There's another way which condensed matter people like to do, and it's very interesting as well. So that I thought that let's do that way. So what they do is instead of doing the second order perturbation theory, they do a similarity transform. They change the Hamiltonian using a similarity transformation. It's not going to change the system, right? Because it's just everything's the same. So So one constraint you put on the new this operator S is that the commutator gives you this. What happens is, if you expand this part and retain the terms only in the second order in MQ, what will happen? You will get just the energy due to the phonons and the electrons in the system. And the second part over here will give you, this is all positive. The only negative thing that can come from is here. Now, this negative energy correction, if you do a slight perturbation to a system and it gives you a negative energy correction, that means that something's wrong. Like this is unstable, right? You have like a top hill potential, and then you do a slight perturbation, it goes on, drops on, right? Something's wrong. So this gives you the instability in the Fermi surface. So this is, I mean, you can extend this and then further you see that there's some instability. This is known as the Cooper instability. And yeah, so one way to maximize the negative part from here is that if you put this term to be zero, this is the energy difference between two electrons that are being scattered. So that will be zero when you have one electron moving with K and the other one moving with minus K. So that's how your Cooper pairing happens. So it's in K space and not in real space. It's not, I mean, people say that, this picture over here that I showed you earlier, that somehow suggests, somehow suggests that electrons are coupled and they attract each other in real space. But that's not really true. I mean, electrons do attract each other, but it's in K space, not in. So they can be really far away, but they are coupled. That's the entanglement that's happening. Okay. These are just the base. I mean, the fundamental things that you find that there are a lot of laws over the internet. So it's not really. Okay. Okay. This is the actual theory that BCS wrote. So it gets really complicated and messy. So instead of that, I mean, to get the exact results, there's a model description also that you can take, which is starting with the Hubbard model. So, but doing some changes to it. This one is just the usual popping term. This one we heard, it says that there's a negative energy contribution from two electrons being at the same side. Now notice that this is again something telling you that okay, so there's negative energy correction for two electrons being at the same side. That means real space attraction, right? So, but let's just transform. If we transform the whole thing to K space, it will again give you the K space this thing. So I mean, this is just the model. So we don't really have to take the whole thing to be very literal. And this one is just the chemical potential. So, okay, so these terms are easy to deal with because they are already diagonal and you can easily diagonalize the Hamiltonian and get the whole thing. But here, this one is what we need to be worried about. So what we do is we just do the Hartree-Fock approximation where we retain these terms also. This is using the base contraction. So notice that in usual case we drop these terms, and that's due to the fact that the ground state is the Fermi surface. And what is happening here is that these are two annihilation operators which will kill two electrons over here, and then this part will come and that will give you zero for a Fermi surface. But since I said that there's an instability in the system, now you know that the ground state is not really Fermi surface, something else. You don't know about that. So that's why you can't really say that this is non-zero. So that's what you keep, and since this is non-zero, you know that something's happening to the Fermi surface. So you can even relate this to the order parameter also. That's how the order parameter is also defined. Something related to this and the conjugative part. So you write down the effective Hamiltonian. Effective Hamiltonian with this defined as the order parameter which is related to this part. Okay, so you start with this Hamiltonian, and then there's this approach by Bogoliubov-de Gennes. So initially we know that the system was diagonalized in the C operators, that means the electronic operators. But now since there are some cross terms and everything, the usual way to diagonalize this is to think of the quasi-particles being a superposition of a hole and an electron. Now these gamma nu operators, they define the operators for excitations and the excitation for a new type of quasi-particle in the system. And they are the superposition. You can invert them and you will see that they are the superposition of these C and C diagonal operators. Right? Now, you don't know what exactly the constraints on U's and V's, these are just the coefficients in the system. So, but you can then find out the constraints by saying that we find this gamma operator diagonalize the system as this And then gamma operators also follow the Fermi-Dirac statistics, which is this and this. So, and these are famously known as the quasi-particles of the Bogoliubov-de Gennes. And that gives you all the constraints for U's and V's. You can solve for that, and then you can get the whole eigenspectrum. So notice now, in the clean superconductor, my whole talk is about the disorder in the system, right? So they are called the dirty superconductors. If we think about this as a clean superconductor, where your T's, where the hopping potential or hopping rates, they don't really depend on the lattice size. They're universally defined. And same for the energy due to this thing, or the effective chemical potential. So if they won't really depend on I's and J's, you can take it out of the sum, and then this can be solved exactly by going to the Fourier transform, Fourier space. But since we have disorder now in the system, we can't really go to the Fourier space. We have to solve it numerically. Okay, so one way to solve it is what we have done is that you start with just the initial guess of what the eigenspectrum would look like, anything. You redefine your Hamiltonian using the self-consistency equation because we're using the mean field theory. Your Hamiltonian is there now, you just diagonalize it with brute force, like the computational thing, and then you get another eigenspectrum. And that eigenspectrum will redefine your Hamiltonian. So you go up to the thing and then change your Hamiltonian and keep doing it until it converges. So that convergence is, this is one of the convergences that you got. It's about some 60 iterations that look like about a minute or something. But it can change when you have disorder, which is more high disorder, or if it's closer to the phase transition, then this thing can go up to 100. Okay, so these are the results that these people got. So the interesting thing happens is that when you go from a normal state to a superconducting state. Now, a normal superconducting, the BCS state is a gap state where you have a gap in the Fermi surface. But what happens is when you have a spin-dependent disorder. Now, what exactly spin-dependent disorder means is that you have there's some disorder and each spin sees it differently. There are some models or experimental techniques to realize such things, and that's in the optical lattice framework and all these things. So you can have this as the experimental thing. But so what exactly you get is that there's a gapless phase appears that there's a superconductor. That means your order parameter has changed, your ground state has changed, but the energy gap, that gap in the density of state is still not there. The gap hasn't really opened up. So there's a gapless phase. That means the energy that you need to excite a Bogoliubov would be just the energy you need to, if you want the Bogoliubov to move with k momentum, that's the energy that you need. So it's like you can think of them as massless particles in the system. But again, when you go down the temperature, again this becomes a gap. So it's a very short-lived phase, and it's very difficult to achieve actually in experiments. So these are just the three kinds of disorders that they have the spin-dependent disorders. That's right. These also say the same thing, that the temperature. This is the change, the drop in the order parameter, and this one is the energy gap, and there's a very small gapless phase, but in the high disordered the gap is bigger. And the same thing when you increase the. So I was writing code for this the whole summer. It took long, and then this is the result. We produced the exact same result. The values and everything, they match perfectly. This is what I did till now. But we will just now we just change the whole system, and then I'll tell about what exactly we're changing and seeing. This is again the whole gapless phase appearing in the whole system. Okay, so now the BCS theory is only for the S wave. What exactly is the S wave? This is, you might have heard about something called conventional superconductors, unconventional superconductors. Conventional are something that is explained by the BCS theory, but actually we have seen some different ideas. Putting to when BCS theory has this interaction with the phonons and electrons. and that gives rise to this S wave. But there are some exotic things that happen as well. It's not just the coupling between this, and that gives rise to other kinds of superconductors, usually the high temperature cuprids and all these things. So we would like to model those as well. So this is one of the things. So you know that if you write down the wave function for a group pair, it should be antisymmetric because it's the electrons. And then if you can just write down the product state of the spin and the angular part, the orbital part. So then there can be different possibilities. If you can have this as a singlet, so the Cooper pair is of the singlet form. There are two possibilities that you have L equal to 0, that is called the S wave, and this is the D wave. And this terminology comes from the fact that the orbitals, they look the same as the symmetry of the system. So similarly, you can have another kind of this thing where you have a Cooper pair that forms a triplet, and there you have this P wave and F wave. So these are very important and topological superconductors, and they're used a lot in quantum computation. And mixture of these things. And it's like they're really exotic things. So this is one of the contour plots in the K space. So S wave looks like this, and on top of it, if I draw the Fermi surface, you see that S wave throughout the Fermi surface, the S wave has the same value. So it's like an isotropic. The gap equation is isotropic basically. But in the D wave, what happens is this is changing over the Fermi surface, and that gives rise to some nodes in the system. And then we've seen that actually some other cuprids have nodes in the system. So this is not really just the BCS. So we need some other theory, the undimensional theory for these kind of superconductors where we do get nodes. So one way to extend this is that you introduce another kind of term where you have the attraction in the nearest neighbor rather than on neighbor, and then you say that on neighbors you have on site there's a repulsion, and nearest neighbor there's attraction. That gives rise to the D wave superconductivity. So this is what we are looking at, and these are the questions that we are posing. That how would one go about defining the order parameters? Because we don't really know. Initially in the BCS state, we knew the order parameters just define on site. Now here it depends on the bond or the nearest neighbor. So what exactly is the correct way to define the order parameter? Because that also takes into account the spin, singlet and doublet, singlet and triplet pairing of the things. So, and the big question is what happens to the gapless phase in superconducting? Because now we are one level down the symmetry. We have even removed the isotropy in the system. So what exactly happens to the gapless phase? Is there something new that's happening? Are there any new phases? Because the symmetry is sort of broken down. And the same thing, like since there's an absence of isotropy, what exactly happens? What are the effects that happen in the system? Okay, yeah, so this is the work that I'm pursuing. So probably by the next year I'll have some good results to show you. But yeah, till now, yeah. Okay, so yeah, thank you.